Hello scientists, this is Dr. B and we're going to talk about Lab 7.4. This is the easy peasy version. There is another more interesting version with more choices, but this is the get it done mode. If you're interested in using an oscilloscope with your own voice, an instrument that you have, some recorded music, your favorite songs, you can do the more difficult version of 7.4. But here we're going to use a frequency analyzer online to analyze things like birdsong, orcas, a police siren, a dial-up modem, which you probably don't know what that is. In the olden days, we had to use a phone to get to the internet. We're going to look at a violin. We're going to hear a person whistling and look at what that looks like in terms of frequencies. We're going to look at a trombone and the frequencies associated with the sound of trombones. And then an optional extra credit is to upload your own file of music. So let's go to the analyzer here. It's right here in this link. We'll just pop right over here. And here is what it's going to look like. You're going to pick a sound here. We'll start with birdsong. And the birdsong is going to show up as a series of kind of globs here. And let's talk a little bit about what those globs mean. You can see there's a bird's note repeated about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 times here. It's that same kind of chirr, chirr, chirr. And so that gives us some information about how the sound is happening kind of over the horizontal. If we look at something like a violin, there's a lot of information here on the vertical level. This is showing all these parallel lines here are showing the harmonics in the violin. Harmonics are when wavelengths kind of like one wave has a different frequency of sound that lines up exactly 2 waves inside that, and then maybe 4 waves inside that. So there are lots of different harmonics here in this violin. If we count, we can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I count 18 different lines, horizontal lines of harmonics, or 18 vertical layers here. If we look across the violin, we can kind of see where someone stops playing for a moment. We can see how the frequency changes. Even though the harmonics, they're altering what notes they're playing on the violin, and we can see that here as they switch notes. So now we have some information from an observation to go to our lab sheet with. So I did the bird song for you as an example. We'll also do the violin together as an example. So there are 18 harmonics, or another way to say that, or 18 horizontal lines that represent different layers of sound in a violin note. And some of that reverberation, some of those harmonics come from that the wood box behind the strings on the violin that reverberates or echoes those notes you make on your violin, creating all the harmonics. If I just take a tuning fork here, which may or may not be able to hear that, it doesn't really have a lot of harmonics. It's kind of more like a pure tone. And so there are differences when we hear just a pure tone versus we hear a musical note that's got a lot of harmonics in it. Something we can say about the horizontal patterns is we can see stops and starts in the horizontal line that represent when the violin is not playing. There's no sound coming out of the violin, and there's kind of like a blank or a stop in the line. We'll go see what that looks like. So right here, somebody stopped playing for a moment, which is okay. It's called a rest in music. It means to stop for a second. So people can kind of enjoy what they just heard. We can contrast the violin with the whistling, which is very different. Excuse me. So let's go violin and let's go down to whistling here. So whistling here only has two clear harmonics. There's one set of lines here, and there's another set of parallel lines here, which makes sense because your human voice doesn't have a wood box behind it like a violin or a guitar or a thumb piano. So we can say some things about whistling. We can say there's only two harmonics. That's kind of the vertical layers that we're talking about. In terms of kind of looking at the horizontal flow, we can see particular notes where the person starts and stops whistling. When you stop whistling, you don't pucker up your mouth. When you are whistling, you pucker up your mouth. And we can hear the person, we can see the different notes. The person's changing the shape of their mouth as they whistle to change the frequencies here. So we can say two harmonics from a vertical standpoint. There is a great deal of non-harmonic frequencies above the highest harmonics. So there's still some noise up there. It's just we don't see clear harmonics. We can see the person make different notes by stopping, by changing the shape of their mouth. Well, we don't actually see them change the shape of their mouth, but we know that the person's making different notes by changing the shape of their mouth, and we know they start and stop whistling from the blank spaces. So where it's just black, that's where the person's not whistling. Let's look at the frequency range here in hertz. We need to look at this scale here, and it depends on the note. Let's advance this a little bit. Some notes go really high, up to, let's say, like 15, 16, let's call that 16 kilohertz. And some notes are really low here. So the range of this whistler seems from about 440 to about 16 kilohertz. So I'm going to go back to our, so got 440 to 16 kilohertz. It's actually probably a little bit below 440. That's just where this range starts. The violin, let's go back and get the range on that. We can see, let's call this 10 kilohertz, and it's between 440 and 10 kilohertz. Let's put that on our sheet here. I'm measuring on this vertical scale here, and a kilohertz is a frequency. So from about 440 or below that, it's hard to tell, to about 10 kilohertz is a violin. Now let's think a little bit about the difference between noise and music. Most people would consider a police siren as noise and not music. It does have a harmonic here. It looks like it has about 4 harmonics. And it has a regular pattern that has a series of notes that are repeated over and over again. And so that's something you could put down for the horizontal observation. It goes up and down, up and down, up and down in a very predictable pattern in terms of frequencies. Of course, sound waves are longitudinal. It's just easier to see them if we make them, if we make the frequency into a transverse wave here. In addition, this police siren, we can see where it stopped for a second, or maybe the recording had a glitch in it. But it's not super interesting. It's just the same thing over and over and over again. So it's a really regular sound, and it has a very predictable range from 440 to 9.7. So police siren, 440 to 9.7 kilohertz. So there's a repeated pattern of changing frequency. Over and over and over. Same pattern of a saw tooth change in frequency. Repeated for the whole recording. The vertical pattern, we can say 4 harmonics, which is surprising because I wouldn't think of a police siren as having harmonics. And we can see those harmonics, and then we see a lot of kind of irregular patterns of frequencies above the last harmonic. So there's just kind of some noise up here that isn't part of the regular sound. So we can say there's a pattern between 440 and 5.1, and then from 5.1 to 9.7, it's kind of irregular smattering of frequencies. So from 440 to 5.1 kilohertz, 440 hertz to 540 kilohertz. I should really put a hertz here. We see regular patterns. And from 5.1 to about 9.7 kilohertz, we see kind of a more irregular pattern. Okay, you can do the orca, you can do the modem, you can do the sad trombone. Basically, you can also talk about what it sounds like. Our class thought the orca sounded like a rusty door or a crying baby. You can come up with your own description. You can tell us what the police siren sounds like, the violin. The optional thing you can do is upload a file of your own music. And you do that by saying choose file and then grabbing a recording here. For some reason that didn't take. There we go.
Hello class, this is Dr. B. I hope you can find some patterns in my voice as you use the frequency analyzer.
So you can see a human voice has some really crazy things going on. There's a bit of a harmonic here. There's a lot of kind of noise because we don't have that box behind our vocal cords, kind of reverberating things. So use your powers of observation, use your observational skills, and fill out the sheet. So just to show you an example of what harmonics are and how you create them, here's a thumb piano. It has a little box behind it. The box has a hole in it. Sound waves can get in here and kind of bounce around. And you can see that when I play one note, kind of echoes. And these blue notes here, they're marked to create more harmonics. If you play them together, it sounds better than if you just kind of play two random notes that aren't blue. We'll go back to two blue ones. That sounds better than, say, the one next to it. So that's how you create harmonics. And I'll put up a recording and we'll look at this in just a second. So I made a recording of the thumb piano on a, it's just onlinevoicerecorder.com. You can just Google record my voice and it's pretty simple to use. So I made that a file and now we'll upload that file into our spectrum analyzer. And we'll see what it looks like.
Okay, here's a thumb piano to demonstrate harmonics. We've got
so you can see there's some pretty clear, the notes are pretty clear and pretty separated, and you can see those harmonics in there. There's a whole bunch of harmonics.
a series of notes. We've got two blue notes plucked simultaneously. Here's another two. Here's two random notes played together.
So the harmonics are a little hard to see because the notes aren't as sustained as on a violin, but you can see there's tons of little parallel lines in here. It's kind of clearer when you see the sort of echo pattern here. But that's how harmonics work. When you have a sound chamber behind your notes, the notes tend to echo and you get more harmonics. So that's 7.4. Fill the rest of it out. Go through the rest of the sounds, including the dial-up modem, the sad trombone, and if you want, you can upload your own files and investigate them. So use your best powers of observation, look at what's happening in the frequency analyzer, and write it down on your lab sheet. Hand in your lab sheet to assignment 7.4. Thanks so much.